Good morning, everyone, and welcome back to Project CD Chronicles, or welcome if this is your first time here. With today's video, I'm introducing a personal project of mine that has reached version 0.1, which I had previously shown you this summer on the channel. Consider this high-level ensemble essentially as a hello world. Let's take a look at it in action right away. This is the version for the Commodore 64, this is the version for the VIC-20, and we also have the version, pay attention, there's no trick, no deception here, for the Commodore 128. As you can clearly observe from the various screens displayed before you, it is evident that all three distinct programs are fully capable of executing seamlessly and without requiring any modifications or adjustments whatsoever the exact same code across each platform. In fact, this is iLevel Assembler. Now, I'm going to show you all the various features of the language, the section on GitHub where the source code is available, possible future developments, and more. I'll be available for any kind of clarification you might need. Alright, let's get back to us. Why do I say it's an assembler? Because we're going to see what it is. Anyway, here we can see that it's already ready in the language. As you can see, these simple instructions, which apparently are high level, are still encoded into a whole series of low-level instructions that, among other things, are easily usable by the end user. In fact, this high-level assembler includes structures that are intermediate between what is a normal assembler, in this case the 64 TAS, and what is a higher level construct, approaching a C-like language where there is a stack, namespaces, and a whole series of features that enable the execution of the code itself. Here, as you can see, we have a stack setup which is very reminiscent of C, dynamic allocation, and calls to internal routines. Of course, all of these need to be coded in order to directly output a character. Where did the idea come from? Obviously, from Randall Hyde, through whom I learned to program in machine language, the 6502, the x86, and so on. In particular, from this innovative project that, years ago, he brought to Webster University, introducing what was a high-level assembler, specifically to be able to use the constructs of Windows and Linux. So, in an assembler, and with very little effort, you could port the same assembler with a very extensive and well-supported library on both compilers. Thank you. So then I thought to myself, why not do precisely the same thing for the 64-bit architecture as well? And that is exactly what I did. You can readily find all of the comprehensive source code on my personal GitHub repository, specifically under the user handle HLA. As you can clearly and distinctly see, it is currently version 0.1, released just a few short days ago. From this initial point, of course, I will diligently continue to improve and enhance it, also based on what my feedback you all give me, and it includes what is an actual library for the high-level assembler. Obviously, it's clear that here there's only a small library, which is the output stage, where it receives a byte and calls what used to be a machine language routine, but it already contains a very substantial set of functions that comes from an old library I had previously written, which is also very well documented. For example, here you have the whole section with the various stacks and how they're used, with the different notations for floating point numbers and so on. And this, so to speak, library refers to a much more substantial library that I'm currently porting, which I had written before, with the difference that this new library will be, thank you, used for both the VIC-20, the Commodore 64, and the 128. Now I'll briefly explain the features of the language. Let's go back to HLA, but we can also see them here in the README, by the way. I initially made a version in Italian. So the iLevel assembler is a high-level assembler that serves as an intermediate point between an assembler, so we can place it here, and a high-level language, so we can put it exactly in the center. This allows us to use an assembler with higher level structures. I still have to code arrays and structs, but clearly, since the basic part is already coded, the whole series of pointers inside is already there. We know that in C, arrays don't actually exist, but pointers do, so in reality the substantial part is already present. what does it require? Obviously, it requires a compiler for C++ that supports the C++23 standard. Consider this as a proof of concept, because from this foundation, I'm already starting to develop a more extensive project. And a part of it, relatively speaking if you like, is related to Node.js, because I compiled the entire compiler in Vasma so that I can bring it online or deploy it anywhere. Also, because I encountered some difficulties with the porting specifically to the Windows version, even though I compiled it while adhering to the standards and set the warnings to level 4 and enabled all checks and errors. The Windows version, however, compiled an executable that, although functional in some parts, produces code that is incorrect, unlike other compilers on Linux. Now let's take a look at some features of the language. For example, I'd like to start right away by showing you, before going through a series of steps, how it works in action and how it's structured. The language is made up of structures and global objects, or in any case, both constants and variables. Of functions, atomic objects such as bytes, it handles both signed and unsigned numbers, and it also manages pointers, including possible pointers to pointers. Now, I wanted to show you this simple step where it takes this assembler. Let's always remember that it's a high-level assembler. For example, these kinds of structures, you see these kinds of expressions. So I ask myself, how easy is it to perform a calculation like this in assembler? And assuming that for obvious reasons this calculation needs to be rewritten with a plus or a minus, how many lines of code would you need to retest just to write this line of code here? And really, in fact, this is exactly where what comes to our aid is the compiler itself and the I-level assemble. Yes, of course, it would also be possible to write them using certain macros. Here, honestly, I don't know, because it's already a local variable on the stack. But if we start writing 2 or 3 macros and then some ifdefs to obviously port it to the Commodore, the VIC20 and especially the 128, and let's also remember that the VIC20 then thank you. Depending on the expansion, the available memory also significantly changes as far as the screen display is concerned. The crucial question is, the code will very soon become completely unreadable, but the definitive answer, quite obviously, is that if we carefully look at what the precise translation of all the assembler code is, and we can clearly see it here in V16, pay close attention, pay very close attention. This specific event happens. Load the accumulator with the numerical value of 1. Okay, pay careful attention, and here is exactly the precise result of this entire complex expression, because the compiler compiles it at the exact compile time. Not only does it fully understand that it needs to perform a typecast, but then a negation operation is automatically and efficiently performed, and it is then placed directly into V16. So basically, this highly intelligent compiler was indeed able to effectively optimize this entire complex calculation process in an extremely efficient and highly optimized way, with very little waste of valuable space and precious memory, and it also does precisely the same for the various operations, of course in a consistent manner. By the way, notice that even the modulo part and so on within the library, many of the operations are already optimized. Let's take a look at a few more examples here, even in this section. By the way, there are also mechanisms for handling some complex structures, like a jump or an if-else, which also checks for the very existence of the label. But more specifically, even within this particular context, I would like to clearly show you precisely what the conversion process to assembler language actually looks like. Alright, moving on. As you can see here, I set it to 1. And if we go directly here, we have a further optimization. If condition is a non-zero constant, generate by block only. And as you can see, this entire remaining part of the else is not considered at all. And this is another optimization step. By the way, I'll also take this opportunity, even though I hadn't included it before, But specifically to show you the compilation process, the compilation process obviously happens through build Linux HLH, so it's really simple. It compiles all of this. And I've also included some batch files, in this case shell scripts for Linux, and it launches what it needs to. And here you can see it. Maybe I'll enlarge it a bit. Thank you. Run test, the program goes through the various stages because it first calls the MCC preprocessor, then it calls the 64, the compiler itself, and then it calls the 64 TAS. Here I compiled it, and as you can see, in the end, it generated the code. It's also possible to Within the documentation, it's also possible to skip the preprocessor and use only the compiler, or to have it call only the assembler. This is all up to your preference. Now, back to us. There are of course many other options within the language. These are just some examples. As you can see here, there are calls with namespaces to standard functions, but also calls, thank you, lower level ones, which I have defined as sys, and unlike the first ones that interface with object types, here they interface, and you can see it's exactly the opposite, directly, in a much more generic way, with words or bytes. Unlike these, which already have a more advanced concept of sign and don't sign, precisely so that in this case they can interface directly with the kernel routines. Thank you. Here we have other examples. Well, here I had done some tests myself, as you can see, with all the various operators. Inside we have clauses regarding the call of assembly, so it directly calls the assembler, and here you can see is the resulting output. I can also easily remove it for you if needed. In this particular case, I take the precise address of the function and then carefully place it into a 16-bit variable. And this is indeed the standard approach, either through the function itself or through what is, so to speak, a direct and immediate call to a kernel function. More or less, these are essentially the same things, and there are many other additional and interesting features that are available. As for the language itself, here too, within the various and diverse components, as you can clearly see here right before your eyes, still within the intricate language structure itself, there is also the direct and explicit use of what is essentially the assembler as is, precisely in its original and unaltered form, just as it is meant to be. Obviously, the language is designed to be as simple as possible. With signed operators, it handles real numbers. Pointers, it handles strings. It is not yet, let's say, it hasn't yet been optimized for string allocation, but this is already planned for future versions. Of course, it interfaces extensively with all the standard libraries designed to port code from the V20, Commodore 64, and 128. Now, however, let's take a closer look at some features of the language, and then, in the final part, we'll talk about Node.js on Windows. I've already talked to you about this part. Some features of the language prevent variable shadowing, because this could lead to errors. Here we have further indications regarding correct usage, in this case with the postfix U16, which tells and enforces to the compiler that it is a 16-bit unsigned number. The ternary operator could have avoided confusion, but I removed it, and that's also a personal choice regarding the use of operators, not so much in relation to C, but rather to adopt a usage more in line with, for example, Pascal. From Pascal, I took the assignment operator, which is different from this one that is actually a constant. I used a question mark for equality, unlike the double equals in C, which could also be confused with this and cause errors. I chose this for the pointer because here I defined the asterisk for multiplication, and so the address symbol is the same as the one used in emails. This way, it doesn't get confused with bitwise operators. The modulo, this is another one that's a shortcut. Regarding the pointer, I preferred to define it in relation to functions, and there's a whole series of bitwise operators that use this initial suffix precisely because it can handle binary numbers as far as TAS, assembler, and octal numbers are concerned, which actually start hexadecimal numbers with S, octal numbers with a % sign, but these are just choices. Some important keywords are indeed implemented, and some specific uses of the various operators are also clearly divided according to their respective category, as well as their established order of precedence. Clearly, here we have the handling of decimal numbers with all the various types of extensions. You can see that binary numbers are managed with 0b and with the percent sign, and we also have an extension for numbers. But actually, this extension is used in C++14. So it is not used by C or by others, but I preferred to introduce it to better write the various numbers. It can also be used with binaries, but this option, like others, is not compatible with MCPP, which is a preprocessor I initially used to make my work easier, even though in the final version it will be integrated directly, and there will be no need to call it externally anymore. As I already mentioned, you can also define various types of constants from the types, and we have all the microprocessor logic. Obviously, there are already some features that we can run, and we can also run them from, so to speak, the operating system known as Linux. For example, if I were to perform the operation minus F32 to F41024.768, we would observe the conversion, and this particular functionality is also a very useful utility provided by the compiler. We have the precise conversion of a numerical value quite clearly. I apologize, you can distinctly see here the minus sign. We have the conversion of a number in 32-bit floating point to the Microsoft format, MB5, and this was one of the shortcomings that didn't allow the 64-TAS assembler to work. It can do it, but it basically does it with the 7154 standard, but only at the compiler level. Here, instead, the entire logic is implemented for converting 32-bit floating points, but also, in this case, 64-bit floating points, which, as you can see, also changes what is, let's say, the last decimal part. All right, let's get back to us. What is required? Obviously, a compiler is required, and here we can maybe go towards the end to the requirements. You see the C compiler or Node.js, which we will see running on Windows, the MCCP for those who want to use the processor, and the 64TAS turbo assembler, specifically to directly compile the code. Now, that's not all, because the compiler also works independently of the platform, since here it is compiled only with Linux and does not work with Windows for the reasons mentioned earlier. So, I compiled a version for Node.js in Wasm, which we are about to see running right now. Alright, now for the more daring among you. I've also included a whole comprehensive set, in this particular case, of various compilation options for effectively utilizing Node.js. Yes. And here as well, I've set up a whole series of batch files, which you can obviously modify as you like, that with a simple batch file or similar execute the various stages of the compiler. In this case, for example, we could go and compile what is the first program, for example, project, which I've already compiled here, project 00, and it will of course compile all the various stages. Where it is located, of course, but here I need to select the Windows part, and here we have the HL64 release. We were in the project folder, and it obviously refers to the bins, to a whole series of binaries and wrapper that allow you to call exactly the version compiled by the preprocessor, the version compiled by the assembler, and the version compiled by the compiler itself in VSM. Obviously, there is a limitation since we are in the project folder, because here it is designed to work from the test folder and the project folder of your processes. He uses a particular technique because he creates a file system in Node and goes directly to fetch the two folders in these two locations. So, if you want to move your project from project to JS, you might need to make some small changes to these types of wrappers, but in any case, it's not essential. What can I say? This is a brief introduction to HLA, High Level Assembler, which is the foundation for a much larger project. I invite you to participate, of course, to give me feedback, and to help fix the bugs and errors that will inevitably be there so we can improve it for the community or for anyone who wants to use it. And that's it. I'll see you on the channel soon with new projects from Project CD Chronicles. For now, I thank you all. Claudio.